Hey, Calc 3 class, we're going to look at an example of a triple integral now in cylindrical coordinates. So we are being asked to find the volume of this underneath this solid 9 minus x squared minus y squared, just a paraboloid that touches the z-axis at 9 and then starts coming down, and the xy plane. So when it hits the xy plane, remember, in that case z would be equal to 0, and if z were equal to 0, we would have, if you move the x squared and the y squared over, we'd have x squared plus y squared is equal to 9, and that of course is a circle of radius 3 down here in the xy plane. So that's what we're seeing down there at the intersection. And we're trying to find the mass of this thing, not just its volume, sorry, its mass, because we're given a density function, sorry. So we're going to use cylindrical coordinates to do this. Now, you have to remember the mass is the density per unit volume, so this is the density. So what we're going to set up is a triple integral over this region of over the region of the density function, alright, dV per unit volume. Okay. Now, in rectangular coordinates, let's look at what this thing would be in rectangular coordinates. So we have our 15z is our density function. So what that means is, as z gets higher, so we go from z equals 0 to z equals 9, right, with this thing. As it gets higher, we are gaining more density for the values of z. So it's getting higher and higher and higher density, you know, as z gets bigger. You know, for these different values of x and y, we get a z, and if that gets bigger, meaning these things are getting smaller, then we get more density. So let's set it up. Well, let me just show you what it would look like if we set this up with rectangular coordinates. Once again, because we got that round base, you should probably be expecting what this thing's going to look like. So we're going to have our density function. Alright, and let's say that we go, the outermost is going to be part of this circle. Let's say that we do, let's do x last. So let's say we'll do dx, and then we'll do dy, and then we'll do dz. Okay? Now remember how these things have to, that's 15z as well. Remember how these things have to work is this is the inside. So this is this integral. And what are the z's changing between? Well, the z's are going between z equals 0, right down here, to z equals 9 minus x squared minus y squared. It's hitting the xy plane, and then vertically it's hitting the paraboloid. So 0 on the bottom, 9 minus x squared minus y squared. Okay, so the outer limits, or sorry, the innermost limits of integration have two variables inside of them. And then this one, this corresponds to dy. This can only have x's. It can't have z's. It can only have x's. So the y coordinates. So once again, as we move between -3 and +3 for x, I'll go ahead and do that. The outermost. These are x's. What are the y's going between? So on one end we're hitting the circle. Remember, this is x squared plus y squared equals 9. So that means that y is equal to the square root of 9 minus x squared, or possibly the negative square root of that. So plus and minus would be the equation of that circle. That's what our y's are running through. You give me an x, and then to get the y, go up to the positive square root and down to the negative square root. So that's what our y's go between. So negative square root of 9 minus x squared. And then up here, the positive square root of 9 minus x squared. So once again, we've got a very ugly integral. It's an ugly integral when we use rectangular coordinates with round bases. So what's the alternative? Remember, we said that when we have round bases like this, to avoid the radicals in the limits integration, we can think of this in polar, and now because we're going up to do this volume, we can think of it as cylindrical. So if I were to, I've already got the r part figured out, so negative x squared minus y squared, this part right here, is negative r squared. Well, I can switch that part right here to 9 minus r squared. That's the easy fix. I'll do my polar stuff in red. Alright, and then instead of dz, dx, dy, I'm going to do dz, dr, d theta. Now when I switch it to polar, remember what we have to do. We have to add on that extra little piece to our integrand, which in this case is the 15z. I have to make it 15z times r. Remember, we have to have r dr d theta when we switch to polar. But the thing is, now my limits integration, I'm not going to have, oops, that's not a eraser. I'm not going to have these ugly radicals anymore. Okay. For my limits integration now, I'm going to have, for r, the second thing, I'm going to go from a radius of 0 to a radius of 3. Now let me give you a little visual. So here's a little visual of how these integrals work when we deal with the polar, the polar definition of the region. So this is our region down the xy plane where we make our intersection, all the points that go up to that paraboloid. So think we're looking down through the paraboloid down at the xy plane. The peak of the paraboloid is right over top of the origin, and then as we go out, we go further and further down until we hit right here. So all the points on the paraboloid that we're trying to find the volume under are encased in this region. Okay, now what happens is how these polar intervals work is, notice it says when r goes from 0 to 3. I'm going to put from 0 to 3 up here. Well, what's happening visually is right now this is r is equal to a. Okay, so I'm going to, this is my angle, 0 theta t. When I sweep the angle around, you don't see anything because right now r is 0. Right, my value of r is 0. Okay, so if I move that up a little bit, just a tiny little bit, and now I sweep the angle around, we're allowing that much of the area to be accounted for. Okay, and then now we do it again. Alright, and then we get a bigger region. You know, we do it again and again, and we get a bigger region. And the more that we put on here, you know, that we add to this, we're sweeping out more and more and more. So we're allowing r to change between these different values, and we're getting all these different points on the in the region. Okay. Now I also have b on here. Let me just show you what b does. B is just an extension over top of a. So whatever a is, whatever a is, if I go out a little bit further from b, this is that idea. You know, I've rotated my circle around, all right, and then I've extended it out. This little idea right here is the idea of delta R. So what do I mean by that? I mean the gap between the previous R and the next R is delta R, just like the gap between, you know, when we made the rectangles with Riemann sums, and we had, you know, this was the old the right end point of the last rectangle. This is the right end point of the next one. That was delta X. It was the gap between them. Well, this is the gap between the R's. All right, and just like before, we could talk about like a limit as, you know, delta R goes to 0. You know, just like we saw with Riemann sums. So anyway, the idea is that we can find volumes with polar, because we can sweep out the region, and we're not having to do it vertically. Oops, we're not having to do it vertically like we do with rectangular coordinates. We can sweep it circularly and just extend our radius until we're out there far enough. So anyway, there's a visual of how what our limits integration are meaning. When I write in here that R is going between 0 and 3, and theta is going between 0 and 2 pi. That's literally what I'm trying to show you with this visual, is that, you know, R is going between, let me put this back to 0. R is going between 0, let me move this up to 3. That we are allowing R to take on all these different values, and theta is going between 0 to 2 pi. It's sweeping out for that radius, and then it's sweeping out for another radius. So R is going to, for every radius between 0 and 3, we're allowing theta to go between 0 and 2 pi. And that's literally what this notation is meaning. Alright, so there's our setup, and now we just do the math. Alright, so the antiderivative of 15zr with respect to z is 15z squared over 2r, and then we're going to plug in the limits integration. So 9 minus r squared is going to go in here for the z. Alright, we're going to square that, and then when 0 goes in, obviously this will go away. So we're going to get what we get when we plug 9 minus r squared into that. Alright, and I brought out my 15 halves out in front. And so I have just z squared, and I'm plugging in 9 minus r squared. So 9 minus r squared squared, okay, is r to the 4th minus 18r squared plus 81. But because we are multiplying by another r in there, we get r to the 5th, 18r cubed, 81r. So that's what we get when we expand it, and now we're integrating this with respect to r. Alright, I got r to the 6th over 6 minus 9 halves r to the 4th, so this is 18, so r to the 4th over 4, 18 over 4 reduces to 9 halves, and then 81 over 2 r squared. Okay, now same thing as before, I'm going to plug in and all these r's, I'm going to replace it with 3. When I plug in 0, it's all going to go away. So when I plug in the 3, that'll get my answer. Well, sorry, the answer for this step anyway. Alright, and then this is just a number. So when I integrate with respect to theta, I'm just going to get theta, and so I'm just going to get this 2 pi. Alright, the 15 halves from out front, the 243 over 2 from the integral, the definite integral for the r part, and then the 2 pi for the 0 to 2 pi that just gets multiplied in here when this just becomes theta. You can see that one of the 2's down here on the bottom will cancel with the 2 from the 2 pi, and we'll end up with 3,645, that's the 15 times the 243, over 2 times pi. Alright, and you can put the pi up there at the top as well. 3645 pi over 2, whatever. But anyway, there is our mass for this problem. Alright, does it give us any units? No units. Okay, so there's our mass. 3645 halves pi.